In the previous video you have seen how we have written Coulomb's law in different situations. Now the formula that we have written for your medium as air, this, and we have called it scalar form. Now the reason why we have called it scalar form was that using this formula we can find the magnitude of the force, that means the value of the force. But clearly, since we know that our force is a vector quantity, it also has direction, hence we are going to proceed and get the vector form of this law. To do that, we have drawn here a system of 2 point charges q1 and q2, let's say located at points A and B. The distance between the two charges is taken to be your r. And to talk about direction, we are bringing two unit vectors which we call them as r12 and r21. Let me show you how we are drawing these two unit vectors. First of all, we are taking an imaginary line joining the centers of the two charges. So I can say that this is the imaginary line and the 2 point charges are lying on this line. Now we know since Coulomb's force is a central force, the force acting on the first charge or the force acting on the second charge should lie on the line joining the centers of these two charges. That means the force cannot be here, the force cannot be here, the force cannot be here or here, but the force is going to lie on this imaginary line. And to talk about the direction in this imaginary line, we need two unit vectors. One you can say is pointing to the right, which is your r12, and one is pointing to the left, which is your r21. Now you could have drawn this unit vector anywhere you want, but we have right now drawn it on the charges. To be more specific, r21 you can say is a unit vector pointing in the direction from the second charge towards the first charge. That's why we have written 2, 1. And r12 is a unit vector pointing from the first charge towards the second charge. And since they are unit vectors, the magnitude of your r21 and the magnitude of your r12 are both equal to 1 units. Now let's say both the charges are similar in nature. That means your q1 is also positive and q2 is also positive. Or let's say q1 is negative and q2 is also negative. In that case, the two charges are going to repel each other and the force acting on the first charge due to the second charge is written as F12 and the force acting on the second charge due to the first charge is written as F21. Clearly, I must draw this force exactly on this charge because this force is acting on this first charge. And this force, which is your F21, is a force acting on the second charge due to the first charge. Hence, we should draw it on the second charge. One more thing to note here is that the two forces that I've drawn just now, I've drawn them of equal sizes because the force experienced by the first charge or the second charge will be same given by this expression. So this is the force acting on the first charge due to the second charge, and this is also the value of the force acting on the second charge due to the first charge. Clearly you can see here the direction of the force F12 is same as direction of your unit vector r21. And the direction of the force F21 is same as the direction of your unit vector r12. Because of which, when we write now the Coulomb's law in vector form, we must write the magnitude of the force, which is this. Force acting on the second due to the first, this is the magnitude, and the direction is r12. So we have written the magnitude and direction. So this is what we call as a vector form. Similarly, when we write F12, we are going to write the magnitude of the force, which is again this, and the direction this time is not r12 but this is r21. Having written this, one change that we can bring in this formula is that the unit vector r12 is found to be equal in magnitude to your vector r21, but they are opposite in direction. So we have a simple relation between them with a minus sign. This minus sign you can write on any side, so I can write r21 must be equal to r12 with a minus sign. When we do that, in our equation B, we simply can replace our r21 unit vector and write it as r12 with a minus sign. And this minus sign can be taken out and placed in front. When we do that, we are going to get this part which is nothing but equal to your first equation here. That means it represents F21. Therefore, we can write the formula for your force F12 or the vector F12 is equal but opposite to your vector F21. And you have seen that this rule, we call it as Newton's third law of motion. To every action force, there must be an equal and opposite reaction force. So you see here, we have found a way of writing Coulomb's law in vector form. And of course, we have used here unit vectors because unit vectors, they help us in giving direction to any vector that we want. And on writing the Coulomb's law in vector form, you have seen that Coulomb's law is found to obey your Newton's third law of motion. After learning your Coulomb's law in scalar form and vector form, the next thing we should study is your superposition principle. This principle is very, very important because every time we may not have a system of 2-point charges, but a system of multiple point charges, because of which every charge is affected by the rest of the charges present in the system. And you have seen that we have written Coulomb's law only for 2-point charges, but not for more than 2-point charges. Let's take up this example. Suppose we have a point charge Q1 located at a certain point in space called A. You can see in this diagram that there is no other charge around this charge Q1, hence the net force or total force on this charge is 0. If somehow I bring another charge called Q2 at a certain point called B, we know that this charge Q2 is going to apply a force on the first charge. You have seen we have drawn an imaginary line joining the centers of the two charges, and we have drawn this force vector in a direction from second charge towards the first charge. That means there is a unit vector in this direction, directed from second to first. Now this force vector that I have drawn has certain length, and that length totally depends on what is the charge on Q1 and what is the charge on Q2. If the charge Q2 was very, very big, I must have drawn a very big arrow showing that the force also should be very, very big. For the time being, let's just have any length. Now, if you ask me, I'll write Coulomb's force acting on the first charge is only due to your second charge. So we have written the formula where this part is the magnitude and this part is the direction. Now suppose in this system, if we add the third charge, you will see that the force on the first charge will not only be because of the second charge, but even the third charge is going to apply force on it. And the force acting on the first charge due to the third charge will be along this line, the imaginary line which is joining the centers of the charge Q1 and Q3. And you can see it is directed from the third charge towards your first charge. And again, as I told you, the length of this force totally depends on the value of your Q3 and of course the distance between these two charges. So I could have drawn it bigger or smaller length, that does not matter right now, but for the time being we'll use this much length. Clearly, if you ask me now, I have to write the total force acting on the first charge must be a sum of the forces acting on the first charge due to the second charge and the third charge. And if you remember, these two forces right now, they appear to have formed the adjacent sides of a parallelogram. So when we use a parallelogram law, I can tell you that the diagonal is going to represent the resultant of the two forces. When we expand this formula, we are going to write the force on the first charge due to the second charge, which is this, force on the first charge due to the third charge, which is this. Here I've written Q1, Q2, here I've written Q1, Q3. Here I've written the distance between the first and the second charge. Here I've written the distance between the first and the third charge. And these are simply the unit vectors. Now one thing you may question is that the force may be attractive as well. In that case, you will see that the sign of Q1 and Q2 will be opposite, because of which the whole direction of your F12 can be reversed, and that is not a problem because our formula already has a unit vector. Our formula has these charges also. Instead of getting R21, if we have opposite charges, we are going to get minus R21. So the formula takes care of the direction of your forces as well. Now suppose similarly, if we have not 3 charges in a system but many such charges, you can see here I have added a 4th charge and so on. We can have many charges, and this is finally we have the nth charge, the last charge. This vector here we have drawn is for the force acting on the first charge due to the fourth charge, and this vector here I have drawn it for the force acting on the first charge due to the nth charge. And again, if you ask me, I would have to say the total force acting on the first charge is equal to the vector sum of the forces acting on the first charge due to the remaining charges, and this is what we call as superposition principle. So let's read the statement once. When a number of charges are present in a system, the total force on a given charge, if you remember we are finding the total force on the first charge, you could have also done it for your second charge, or you could have also found the total force or net force on the third charge or fourth charge or any charge you want. Right now we are talking about only the first charge. So when the number of charges are present in a system, the total force on a given charge is the vector sum. You can see it is a sum because we are adding all these forces, vector sum of the forces due to the remaining other charges, and of course these are the forces acting on the first charge due to all the remaining charges, the second charge, the third charge, the fourth charge, and the nth charge. You will see the superposition principle is going to become very handy in solving many numericals. Let's expand this formula. When we expand this, we are going to get this with all the unit vectors in their correct places, with all the distances of the charges from the first charge, and of course the magnitude of the product of the two charges. Now in all the terms you can see q1 is common and 1 by 4 pi epsilon naught is common. However, this part is not common. This part can be written as a summation over I, where our I starts from 2, because if you look at the charge, our charge here is q2, q3, goes on up to qn. So we have written qi such that the charge starts from q2, q3, q4 and goes up to qn. Here we have written r1i squared. We have done that because we are going to find the distance of the first charge from the second charge, distance of the first charge from the third charge till we reach the nth charge. And finally this must be here unit vector directed from the ith charge to the first charge. It's like saying directed from the second to the first, third to the first, fourth to the first. So you can see we have a simplified formula to write this big expression. You will see you are going to study electric field as well. There also we are going to use a similar rule of superposition principle. That time it is not going to be addition of forces, but that time it is going to be addition of electric field intensities. Let's solve this problem now. Given here are 4 charges of magnitude 4 microcoulombs each, placed at 2 meter mark, 4 meter mark, placed at 0 meter mark, 2 meter mark, 4 meter mark and 6 meter mark along x-axis. The question is we have to find the net force acting on a charge which is placed at 0 meter mark. Clearly you can see we have written all the charges are 4 microcoulombs, which can be written as 10 to the power minus 6 coulombs. This is the 0 meter mark, the 2 meter mark, the 4 meter mark and the 6 meter mark. And we have charge q1, q2, q3 and let's say q4. The question is we have to find the force acting on this charge which is placed at 0 meter mark. And since all of them are positive, if you recall, the first charge will be repelled by the second charge. So we will have a vector in this direction and that vector will be called F12. So this is going to be our vector called F12, the force on the first due to the second. The third charge is also going to repel the first charge because again they are positive. So the first charge will be repelled by the third charge again in this direction. This time I can say I have a smaller vector because you can see the distance between the charge q1 and q3 is bigger. That means the force is going to decrease. And this force this time I have to call it F13. And finally again the q4, which is positive again, will apply repulsive force to this first charge which is positive, but the force is going to be less because the magnitude is same as other charges but the distance is very large. So we have another force in this direction which we call it F14. So in this system where there are 4 charges, there will be 3 forces acting on the first charge One is due to the second charge, the other due to the third charge, and the last force will be due to the fourth charge. That's why we have written the superposition principle as net force acting on the first charge equal to F12 plus F13 plus F14, the vector sum. If you look at this diagram, all these three forces that we have talked just now all have direction of your negative I cap. Hence, when we write or expand this formula, we have written minus I, and minus I as the direction of all those forces. Then, force on the first due to the second has been written as Q1, Q2 by distance between the first and the second, which is your OA. The distance between the first and the third is written to be OB, and the distance between the first and the fourth is written as OC. And here you can see in the second term we have multiplied the first charge and the third charge. In the last term we have multiplied the magnitude of first charge with the fourth charge. Clearly you can see 1 by 4 pi epsilon naught is constant or common. The changes are Q1 is common, minus I cap, which is the direction of the net force, also is going to be common, and we have this term. We are simply going to put the values. Your job is to fill up this blank. Send in the group what do you get out of this. In this new problem we have 3 point charges. One is plus 5 microcoulombs, the other is 10 microcoulombs, and the last one is minus 10 microcoulombs. They have mentioned the medium in which these three charges are present, and they have said that these charges are present at the corners of an equilateral triangle, and the equilateral triangle is found to have a side of 5 centimeters. The question is, we have to find the resultant force or total force acting on a charge located at point A. When we draw the diagram, you can see we have a triangle A, B and C. The charge located at A is plus 5 microcoulombs, charge located at B is plus 10 microcoulombs, and charge located at C is minus 10 microcoulombs. Clearly, we have to find the force on this charge. Now, who's going to apply force on this charge? The remaining charges, and the remaining charges are your Q2 and your Q3. The force applied on the first charge by the second charge should be in this direction, because you can see both the charges are positive in nature, hence the force between them will be repulsive. That's why we have drawn a force arrow in this direction representing the force on the first charge due to the second charge, and of course we have drawn it of certain length. Now that length depends on the magnitude of these two charges and the distance. The magnitude is 5 here, the 10 is the magnitude, and this distance is 5 centimeters. Again, if you find the force acting on the first charge due to this charge called the Q3, you can see it is negative in nature. Definitely this charge is not going to apply repulsive force on this first charge, but is going to apply attractive force, because of which the first charge is going to be pulled in this direction by your third charge, because you can see one is positive and the other is negative. And why we have drawn these arrows here and not here? Because we are not finding the force on Q3, we are finding the force on Q1. That's why we are drawing these force arrows on Q1. Again, if you notice, I have drawn the length of your F12 and F13 to be same. The reason is simple. The value of F12 and the value of F13 is going to be same here, because the distance between first charge and second charge is same as the distance between the first charge and the third charge. The product of Q1 and Q2 will be same as the product of Q1 and Q3. Hence the magnitude of the force, which depends on the product of the charges and the distance, are going to be equal. Hence we have drawn them of equal sizes. Now when we do that, you will see that these two vectors are going to make an angle of 120 degree between them, and the resultant force will be exactly in between them as given by your parallelogram law. And we know, since it's an equilateral triangle, this is angle 60 degrees, so definitely this angle here, and definitely we must have an angle of 120 degree between the forces F1 and F3. F12 and F13. Now, how do we write the total force? Here you can see we are not using any I cap or J cap or K cap. That's not required right now. You can still do this problem without the unit vectors. We have written Q1, Q2, Q3 in your SI units. We have written the R, which is 5 centimeter in meters. Then we have written the force on the first due to second, which is this formula here we have. And we found it to be 180 newtons directed along BA. That means from B towards A, this one. Then we have force on the first charge due to the third charge, which is this. We have written the same formula, but this time we have Q1 into Q3. The distance is R again because it's an equilateral triangle, so we have same distance between the three charges. And again we are going to get, you can see, 180 newtons. This time is directed along AC, from A towards C. Now if you remember, we are trying to add F1(2) and F1(3) to get the resultant force. And we know a rule which we call a Sparrow Graham Law, which can be used because we know the angle between these two forces. Here I must have written F1(2), force on the first due to the second, and force on the first due to the third. So please make the change in your notes as well. When we do that, we have written here 180 square twice 180 into 180 and cos of 120 degree. Cos of 120 degree is minus half. On solving, we are going to get force of 180 newtons total acting along a line which we have represented by AX. That is this. Let's discuss the next problem here. The question is, there are 4 point charges, each of 16 microcoulombs, placed at the corners of a square, and the square is found to have a side of 0.2 meters. The question is, calculate the force on any one of the charges. Now here clearly they have not mentioned the nature of the charges. When they do that, just take them as positive, all of them. Now we have a diagram for that. You can see we have a square called ABCD. We have written charge Q1 here, Q2 here, Q3 here, and Q4 here. Let's say we are going to find the net force on this fourth charge due to all the remaining charges. So the force on the fourth charge due to the first charge will be this, because they are going to repel. So this is the force acting on the fourth due to the first. It is acting along the line joining the two charges, which is this. The second charge is also going to repel this fourth charge, and it must be along this diagonal away from the second charge. So we have just drawn that, and actually I should draw it a bit small in size, because you know that this diagonal is going to be very long compared to these two sides. So the distance between the fourth and the second charge is quite big, because of which this length of this arrow should be drawn smaller than compared to your other forces. So we are going to call it force on the fourth charge due to the second charge. Then finally we have your force acting on the fourth charge due to the third charge, and that also must be repulsive. So we have that force along in this direction. Clearly you can say that the angle between your F43 and F41 must be 90 degree. And since this line here is the diagonal, and we know this is going to be 45 degree, obviously this angle here also will be equal to 45 degree. 45 degree. To solve this problem, first we'll write the values of all these forces, which is F41, F42 and F43. So let's do that. So we have written the formula of the force between the fourth charge and the first charge. The distance is 0.2, so you can see we have written 0.2. We have written 9 to 10 to the power 9. 16 into 10 to the power minus 6, again 16 to 10 to the power minus 6. And the answer comes out to be newtons, to be this much. This force is acting along AD. For your F42, we have written the charge, we have written 9 into 10 to the power 9, and the distance between your second charge and fourth charge is your BD. Now if you look at this diagram, this distance is 0.2 meters, this distance is 0.2 meters. We know square, so this is your right angle. This must be the hypotenuse, and we can write the hypotenuse, which is your BD square, must be equal to base square plus perpendicular square. Hence in place of BD square, we have replaced by base square plus perpendicular square using Pythagoras theorem. Then on solving we get the value of 28.8. As I told you, this force will be less compared to the other forces, and you can see the number as well. Now this force is acting along BD. Finally we have the force acting on the fourth charge due to the third charge, and that must be in this direction. So we have written the magnitude of the two charges and we have divided by the distance squared, and again we get 57.6 newtons. This force is found to act along CD. Now in order to add the three forces, you must remember that we just cannot come and add them because they are not scalars but they are vectors. And vectors to be added, we must follow some rules. First, we will just add F41 and F43. The reason is F41 and F43 are found to be at an angle of 90 degree and it's very easy to add them. And they are also equal in magnitude, because of which the resultant of F43 and F41 will be along this direction, same as direction of your F42. So I'll repeat again. F43 and F41 are equal in magnitude. They are acting at 90 degrees, because of which the resultant of these two will be exactly the bisector of both of them. And that bisector is found to be in same direction as your force F42. So this is the resultant of your F41 and F43. When we do that, we must write magnitude of F41, magnitude of F43, twice the magnitude of F41 and F43, and we must write cos 90 degree. But we know that cos 90 is 0, so we are only left out with this part. On solving, we are going to get 81.5 newtons, and that is in the direction of your F42 as I told you. Now clearly F42 and the resultant of these two forces, since they are in same direction, the total force or the net force I can say is that add the net force between these two charges with your F42. And why we are adding is simply because they are in same direction. If they were in opposite direction, you can see we have to subtract them. So when we do that, we are going to get 110.3 newtons. This problem you try to solve and send in the group for the others to see,